And it's always, honestly, just an enormous pleasure to be part of the Green Cover team and to have this opportunity to talk about one of my favourite topics, which is nitrogen. So if I can, we're going to have a perfect day today where everything is going to go absolutely
flawless. It's going to be a flawless presentation.
It's going to be a flawless presentation. That's it, Noah. So what you can see in front of you there is a dinitrogen molecule. In other words, two atoms of nitrogen bound together by a triple bond. And this is the form that nitrogen occurs in the Earth's atmosphere. And I'm going to talk about that in more detail in a little moment. Last week we talked about phosphorus fertiliser, and the points that I made about phosphorus is that it's relatively immobile in the soil. In other words, wherever you put it, that's pretty much where it stays. Only about 10 to 15% of the phosphorus fertiliser that is applied is taken up by plants in the year of application, which means that 85 to 90% of our fertiliser additions are immobilised. In other words, they're fixed in the soil, they're bound. Phosphate has a negative charge, it's highly reactive, and it is going to bind with elements in the soil that have a positive charge, such as iron and aluminium. Did you hear me how well I said that? and in alkaline soils with calcium. And even though a lot of the phosphorus that farmers have added to their soils has not been taken up by plants, provided they haven't lost the soil through erosion, they have now actually formed a large phosphorus bank. And that phosphorus is going to be able to be accessed at some later stage using microbial intermediaries, and we'll talk about how we're going to activate the soil microbiome. So you haven't actually lost that unless you have lost the soil. And if you've been using phosphorus fertiliser, the good news is that most of it is still there, and you can access it later. The news with nitrogen is not so good. Nitrogen fertilisers, I'm talking about inorganic forms of nitrogen now, like nitrate and ammonium. It's highly mobile in soil. It doesn't actually bind to soil particles and stay there. Only about 10 to 40% of the nitrogen that's applied as fertiliser is taken up by plants, usually because they're just not able to take up such massive amounts of nitrogen, particularly if it's applied like pre-plant. In fact, sometimes in Australian situations, we've seen where quite a lot of nitrogen has been like preloaded, sometimes like say 6 weeks before a crop is planted, and we go and measure the soil the day that the crop's being planted, and none of the nitrogen that was preloaded is there. It's all gone by the time the crop is even planted, and then that, of course, the seedlings come up and they're nitrogen deficient. But even under ideal conditions, somewhere between 10 to 40% is taken up by plants. The other 60 to 90% goes somewhere else, into the water, up into the air, and it's going to cause a problem. It's a very significant environmental pollutant all around the world. And nitrogen is very rapidly transformed. It occurs in several different chemical formations, and it can move from one of those to another one very, very quickly. And it does not, the nitrogen fertiliser that you apply to your soil does not accumulate and form a nitrogen bank like a phosphorus fertiliser does. In fact, the more nitrogen fertiliser you use as a general rule, the less nitrogen you have in your soils. Now, if we're looking at this in terms of energy use efficiency and fossil fuel use, all those kinds of things, the production of nitrogen fertiliser is a very highly energy demanding process, and it uses 6 times more energy like per tonne of fertiliser than the production of phosphorus fertiliser. And producing nitrogen fertiliser also emits large amounts of methane, which is another greenhouse gas. So if it is possible for anything to be more detrimental than phosphorus fertiliser, then nitrogen fertiliser is it. So why do we use it? Well, Keith, in his introduction to last week's webinar on the phosphorus paradox, said we're never going to run out of nitrogen. And that is just so true. But 78% of the atmosphere is dinitrogen, which is that molecule that I showed right at the beginning. Two nitrogen atoms covalently joined with a triple bond. That means in metric terms that we have 78,000 tonnes of nitrogen gas sitting above every hectare of land. And I did do the math on that. That equates to 70 million pounds per acre. So we have 70 million pounds of dinitrogen gas sitting above every acre of land. There is really no need to go out and buy it, especially when we see all the downsides of using inorganic nitrogen fertiliser. But the problem is that all of that nitrogen that's in the atmosphere, that dinitrogen, is relatively inert and it's not directly available to plants. Sometimes you'll hear people say, legumes, for example, can fix nitrogen. Well, legumes can't fix nitrogen. Legumes can form a symbiotic relationship with rhizobia bacteria that can fix nitrogen. So it's always going to be a microbe that's in association with the plant, not the plant itself. And so as with phosphorus, as we discussed last week, it's going to be microbes and their enzymes. It's going to be microbial enzymes that are going to be the key to accessing nitrogen. And in this case, the microbes are called diazotrophs. The diazotrophs are bacteria and archaea that are able to break that triple bond between two nitrogen atoms and actually convert that relatively inert dinitrogen, which is why they're called diazotrophs, into a plant available form. But the trick here is that diazotrophs utilise the enzyme that they use is called nitrogenase. There are a whole range of nitrogenases. Sometimes they're called dinitrogenase and sometimes they're called dinitrogenase reductase. But basically it's a group of enzymes called nitrogenases. And those that is the enzyme that breaks that bond in the inert dinitrogen gas. But nitrogenase, the enzyme that microbes use, is inhibited by oxygen. So the only place in the soil or in a plant where diazotrophs are able to break that triple bond and convert inert dinitrogen gas into nitrogen in a plant available form is in specialised what we call microaerobic fixation sites. In other words, microaerobic means there is a little bit of oxygen there, but not a lot. It's not anoxic and it's not anaerobic, but it's not aerobic either. It has a low partial pressure of oxygen. And these specialised fixation sites are inside rhizosheaths and inside water-stable aggregates. So if we want to know whether our plant community or our soils are able to fix nitrogen or able to support free-living nitrogen-fixing bacteria and archaea, we just need to look to see whether the plants have rhizosheaths or whether water-stable aggregates are forming in that soil. And if you are building topsoil, if you have evidence when you go out with a spade, dig a hole, like visual soil assessment is going to tell you a lot more than sending a sample to a lab. You need to look to see, are these things happening in my soil? Do my plants have rhizosheaths? Is whatever it is that I'm doing, is it forming water-stable aggregates in this soil? Can I see evidence of aggregation? And if you can, if soil building is taking place, then nitrogen fixing is taking place because, as I explained last week, the humic molecules that are involved in that whole soil building process are a combination of carbon and nitrogen in the same molecule. So you know that nitrogen fixing is happening if you're building soils. And that's probably all you really need to know because that will certainly tell you more than a lab test will tell you. The bad news is that the formation of rhizosheaths on our plants and the formation of water-stable aggregates is inhibited by the use of high-analysis inorganic nitrogen fertiliser. So what do I mean by inorganic nitrogen fertiliser? I'm talking about things like nitrates, ammonium, products like anhydrous ammonia or urea or nitram, anything that's got any form of nitrate or ammonium in it is going to be an inorganic nitrogen fertilizer. And if a lot of that is applied, and I'll talk about at the end of this presentation, I'll talk about what I mean by a lot, because in actual fact, a little bit can be stimulatory. It's one of those things where the concentration effect is very important. But if people are using high amounts, and I mean, if you're using anything, over 50 pounds per acre, it's too much. And it is actually going to inhibit rhizosphere formation and the formation of water-stable aggregates. So then natural free-living nitrogen fixing can't happen. So in other words, the more we use it, the more we use nitrogen fertilizer, the more we lose it. And there's plenty of research evidence around that. And the unfortunate thing about the research, there has been millions of dollars of money go into research into nitrogen dynamics in agricultural soils. Every year there's probably millions of dollars spent. And every year farmers around the world spend over $100 billion on nitrogen fertilizers. And all this research and all this money that's spent on fertilizers is mostly under conditions that are not supporting the activities of free-living nitrogen-fixing bacteria and archaea. So if you're reading a paper about nitrogen dynamics in agricultural soils, and, well, for a start, if synthetic or high analysis inorganic nitrogen fertilizer has been applied, then what you're looking at is irrelevant to a situation that's going to be supportive for free-living nitrogen-fixing bacteria. If the research was conducted in soils that have been kept in storage for a long time and they're not biologically active, the results of that research are going to be virtually meaningless. If the research is being conducted in a monoculture, the results of that research are going to be virtually meaningless. In other words, we can probably discard about 99.9% of the research that's ever been undertaken into nitrogen dynamics in agricultural soils. So we have to go back to ground zero and start again, and look at this with a totally, like, we do need to start with a blank canvas and figure out what is actually going on in our soils. Now, I showed this photograph last week or the week before, but this is what a lot of scientists will see when they're studying plants in the glasshouse or in the laboratory. They'll see plants that have clean white roots like that, which means that they're not looking at plants in a situation that is going to support free-living nitrogen-fixing bacteria and archaea, because there is nowhere in that environment for nitrogenase, the enzyme that is going to convert atmospheric nitrogen into a plant-available form. There is nowhere in that environment for nitrogenase to be able to function. Remember, it's inhibited by oxygen. So if we have clean white roots like that, no rhizosheets, there is not going to be any nitrogenase active. So here are some photographs taken in the field. This is a fence line comparison. On one side, on the left-hand side, we have a farmer that has been using a nitrogenous fertilizer under an oat crop. And on the right-hand side, we have the same soil, the same crop planted at the same time, everything the same, where they have not used any nitrogen fertilizer. And you can see the difference. On one side, we have bare roots. There's going to be lots of oxygen around those roots, and it's not possible for free-living nitrogen-fixing bacteria to help that crop. On the right-hand side, we have the formation of aggregates around the roots. You'll also notice there's fungal hyphae in that photo, and fungi are very important. They're plant-associated fungi. They're supported through that fungal energy channel that I'm going to mention a little bit later. Very important for creating the structures in soil that we need for free-living nitrogen fixing to take place. This was something that really brought the whole issue home to me very, very clearly. This is Sara and Ilka in Finland, and they were converting their farm to organics, and they were doing a trial with something like 20 different organic fertilizers that were all carbon-based fertilizers, like different kinds of compost. And we were looking at the roots of the wheat plants to see whether these fertilizers, these biological fertilizers, what difference they were making to the rhizosheets on the plants. And what we found was that every single one of the 20 treatments that we looked at had beautiful rhiza sheaths on the crown roots that were the roots were coming out of the crowns of the plants, but below the seed, all of the roots were completely white and clean and had no soil sticking to them whatsoever. Hello, it's just done that to me, jumped over. Keith's given me instructions on how to operate this when it happens. Okay, so we have our wheat seed here, and these amazingly clean white roots, seminal roots coming down from the seed. Didn't wash these plants, just dug them out, shook the soil off them, and these beautiful rhiza sheaths on the crown roots. And I've never seen it like that before. And here's another one. Here's the seed here. These are incredibly clean roots, and these beautiful rhiza sheaths here, all on the same plant. And I was just totally puzzled. I couldn't figure it out because they were converting to organic, so I assumed that they weren't going to be using any nitrogen fertilizer. And we went back and had some lunch and talked about it. And in the end, I said to Sarah, look, you haven't used any nitrogen fertilizer here, have you? And she said, oh, yes, the scientist that was helping us set up this trial and conduct this research in a way that was going to give us meaningful results, said that because these biological fertilizers that we were using, which was a range of different kinds of compost, had different carbon to nitrogen ratios, and in order to take that out of the experiment as a factor, we needed to apply nitrogen to everything to equalise the amount of nitrogen in the plot. So all of the treatments had 80 units of N placed under the seed. So if you want to see what nitrogen placed under the seed does to wheat roots, there it is, absolute classic. Here are the seeds, nitrogen placed under the seed. There is no possibility for any nitrogen fixing to happen in that environment. But up here, where the crown roots are in contact with the various forms of compost that they were using, beautiful rhiza sheaths, and there will be free-living nitrogen fixers living inside those rhiza sheaths because it's a micro-aerobic environment, a low partial pressure of oxygen. And in fact, if nitrogen hadn't been placed under these seeds, there would have been rhiza sheaths on these roots here as well. So in the secrets of the soil sociobiome 2 weeks ago, I talked about the fungal energy channel, and I showed this photograph. I think I've probably showed it every time. I might even show it again next week. I just love it so much. So over here on the left, we have a plant root, and on the right, we have soil particles. And this is what we would be able to see if we used a microscope to look in underneath or look into a rhiza sheath. We'd see all these fungi, these fungal hyphae that are extending from the plant root out to the rhiza sheath. And of course, they're helping to bind the cell particles that are clinging to the roots to create that rhiza sheath in the first place. But this space inside here, this is going to be a low oxygen environment. It's going to be low partial pressure of oxygen in here, and they're going to be literally trillions of bacteria and archaea, all feeding on root exudates, but also even some of them will be forming biofilms on the hyphae of these fungi. And it's a very, very rich environment for free-living nitrogen fixers. Now, if you think about it, we have this belief that, number one, we have to add nitrogen for plants to grow because we know that they do need nitrogen. And number two, that legumes are the only plants that form a relationship with nitrogen-fixing bacteria. Well, if you really think about that, if legumes were the only plants that were able to form a relationship with nitrogen-fixing bacteria, they would probably be about the only plants that would be on the planet because no other plants would be able to survive. And yet you can go to plenty of environments and look into the plant community and see there are no legumes there. And everything else is nice and green and everything else is growing perfectly well. So obviously every single green plant has the capacity to form a relationship with free living nitrogen-fixing bacteria. Otherwise it couldn't be green because the chlorophyll, the pigment that makes a plant green, is actually part of a protein complex. So it can't be green unless, or can't contain chlorophyll unless the plant is able to access nitrogen from somewhere. So the plant is going to access that nitrogen through microbial intermediaries and they need a specialised environment in which to thrive. They need an environment where there's lots of energy coming in, and that energy is going to come through that fungal energy channel through plant root exudates, and they need some kind of a structure like a riser sheath or a water-stable aggregate that's a root-supported water-stable aggregate. In other words, it's going to be fine feeder roots coming into that aggregate and actually building that aggregate. And in those environments, the plant is going to be able to obtain all of the nitrogen that it needs. And I think I also used this slide last week. This is just the brown bit down the centre is actually a plant root, and all the creamy, the network here are the hyphae of, in this case, ectomycorrhizal fungi, but there are a lot of the other fungi that are in soil we can't see with the naked eye, or even under a microscope we can't see them, and yet this is what it's going to look like in the soil when the fungal energy channel is open and operating. So these fungi, these fungal hyphae, are going to be taking energy that was derived from photosynthesis that the plant has channeled down to its roots and is pumping out into the soil sociobiome through these fungal hyphae. It's going to be taking that energy out to colonies of bacteria and archaea that are going to be able to fix nitrogen in water-stable aggregates. And so the plant-associated fungi in this fungal energy channel are going to be transporting energy to nitrogen-fixing bacteria and archaea, because remember that production of the nitrogenase enzyme and the breaking of that triple bond actually requires quite a lot of energy. And they're also going to be transporting organic nitrogen back to plant roots. So there was a question came up, I'm not sure whether it was last week or the week before, about are fungi able to fix atmospheric nitrogen? Well, the answer is no. But fungi are very, very important. Plant-associated fungi are very important for bringing nitrogen back to plants. And they will bring it back in the organic form. They're going to bring it back as amino acids. And the reason they transport it as amino acids is because that is the most efficient way, energy-efficient way to transport them. And then once they're inside the plant can very easily assemble amino acids into complete proteins. It doesn't take much energy for the plant to make all the proteins that it needs from amino acids. If the plant takes up inorganic nitrogen, as we are led to believe by just about every textbook that you read about nitrogen, will say that plants prefer to assimilate nitrogen usually as nitrate. Nitrate would be the preferred option, and then ammonium would be the second preference. Well, that's actually not true. That's only because people have looked in environments where that's really been the only options that plants have had. If they take inorganic nitrogen up into the leaves and the stems, they then have to produce a whole lot more carbohydrate to add to that nitrogen, that inorganic nitrogen, to transform it into amino acids and into protein. Is a huge metabolic cost to the plant to transform inorganic nitrogen into protein, and often the plants are not able to do it. So the nitrogen remains in an inorganic form in the plants, and that's when we have livestock that suffer from nitrate poisoning, or we have even metabolic issues in livestock from consuming plants that are very high in nitrates. We actually don't want any nitrate in soil, in plants, in our animals, or in our water. And the way to avoid having nitrate in any of those environments is not to use it in the first place. And if we are supporting that whole fungal energy channel and that soil sociobiome, even though the bacteria and the archaea are going to fix nitrogen as firstly as ammonia and then very rapidly convert that to ammonium, it is then going to go into the microbial biomass. It's going to be part of the bodies of all the things that live in soil, and it's going to be in that microbial biomass in the amino form. So it's going to be organic. It won't show up on a soil test as available N, and I have seen multiple soil tests where the soil has virtually no detectable N. A leaf test will show that there's virtually no inorganic N in the leaves, And if an agronomist looked at that soil test and that leaf test, they would say this plant is not capable of producing anything. And yet those particular plants will have some of the highest grain yields in the district and the highest protein content in the grain in that district. And that is because in the soil and in the plant, the nitrogen was in an organic form. It's not leachable, it's not mobile unless it's transported by fungi, and that is the form we want all of our nitrogen to be in. And it will be if all we need to do as farmers is support that fungal energy channel. I've also said multiple times in the past that 85 to 90% of plant nutrient acquisition is microbially mediated. It's because I like using lots of big words. But even when we apply synthetic fertilisers to soil, as a general rule, they cannot get into plants unless there's some kind of transformation takes place in the microbiomes. The microbes are just so incredibly important for plant nutrient acquisition. And as I mentioned last week or the week before, we need lots and lots of different kinds of microbes living in all the different compartments, if you like, of the soil and the plants. We want microbes around the rhizosphere, we want microbes in the stems and the leaves, the fruits, the flowers, and we actually want the plant to incorporate microbes into its seed and carry those through to the next generation in its core microbiome. And ideally, a lot of those microbes would be bacteria and archaea that have the ability to fix atmospheric nitrogen. And they're going to interact with a whole lot of other microbes that are in that sociobiome, because it's never a case of one single microbe acting alone. And this has been the issue with there has been a lot of research into things like name's just gone out of my head. It's not Azotobacter. Is it Aspergillus? Aspergillus, I think that's right. Gosh, that date of birth is really having... Never mind, Christine. There's been a lot of research into trying to isolate individual nitrogen-fixing bacteria or even individual clones, if you like, or isolates of some that are better able to fix nitrogen than others, even within one species of nitrogen-fixing bacteria. But a lot of that has not come to anything, because you can't just apply one species of bacteria to soil or one species of bacteria to seeds or to plants and expect it to be able to function. It requires bacteria workers teams, or bacteria and archaea and fungi, everything that lives in soil works together. It is a sociobiome. We just need to create the right conditions for all of those bacteria to work together, and we'll get the desired result. And we have to remember what I have already mentioned before is that we want different kinds of plants that have different functional traits. In other words, they come from different plant families. Because if the microbiomes of all of the plants that are growing together in a community are similar, in other words, if we have a monoculture of something, then the microbiomes have a negative feedback effect on nutrient acquisition. A microbiome will recognise that the neighbouring microbiomes are the same as it, and it will not cooperate with those neighbouring microbiomes and will be very competitive for nutrients. If we have dissimilar microbiomes, in other words, we have plants with different functional traits, they're from different plant families, growing together in a community, and the microbiomes of the plant detect that the others around it are different to itself or dissimilar to itself, there will be a positive feedback on nutrient acquisition, and plants will actually exchange nutrients through the common mycorrhizal network and will help each other. So some plants that are able to, like there might be some plants with deep taproots that are able to access minerals from the subsoil, while others have shallow fibrous root systems, not able to access those same particularly trace elements. Those things can be shared through the common mycorrhizal network, provided the plants have dissimilar microbiomes. So it's really important that we look at those functional groups. And in our mixtures, this is some plants that you may put in a pasture, but in our cover crop mixes or in our companions, we need to look at having different plant families to obtain the best outcome in terms of nitrogen fixing. So we could have a plant community. I know that there are legumes in that particular diagram. So we have plantain, red clover, chicory, pea, ryegrass, lucerne, which you will call alfalfa, beets, fescue, dandelion, and cocksfoot in that diagram. I'd like to see a lot more diversity than that, but it's that's a start. And quite a few of those things are legumes. Red clover, pea, and alfalfa are legumes, but we could take the legumes out of that system and just have, if we have at least 4 plant families in there, it will be equally as good at fixing nitrogen. In fact, diverse systems with no legumes, provided we have 4 functional groups, at least 4 functional groups, will fix more nitrogen than a system with legumes. So people talk about how many species should I have in a mix, and, maybe 6 species in a mix or 8 species in a mix. And I say, well, if they're all legumes, it probably will have a negative effect. You want, 4 plant families and 2 species from each or something like that. So here's a practical example of that. This is, I saw this in a cover crop demonstration on a research farm in Ontario, in Canada, and there were strips probably about 20 yards wide, I guess, of a whole lot of different cover crop species planted as monocultures, and then mixes of those right up to something like, I think, a 12-way mix. So in this example here, we're looking at just radish grown on its own, and all of these plots actually received a base application of an NPK fertiliser. So it has been fertilised, but it's very nitrogen deficient. And right next to it, on the right-hand side, was a mix of radish with, or planted at the same time, everything the same, radish with a little bit of oats and sunflower and phacelia. So you can see the radish leaves in here are all beautiful and green. I'm sure you all recognise oats. There's a phacelia plant here and sunflower here. So what we have is not a huge amount of other things in there, just a smattering of other kinds of plants in there, but we actually have 4 plant families in that particular case. So even though in this research they were looking at all these different combinations and different mixes, there wasn't any emphasis on functional dissimilarity. It just so happened that in this particular case, there were 4 plant families in this mix, and there is no obvious signs of lack of nitrogen. And the other interesting thing about this photograph is there are no legumes in this mix. So we have sunflower in Asteraceae, oats in Poaceae, radish in Brassicaceae, and phacelia in Boraginaceae. We don't have any legumes in there, and there is no nitrogen deficiency. So if I just splice those photos and put them side by side, you can see the huge difference. Plants were much larger, and obviously not nitrogen deficient, and yet the whole trial received the same basal application of nitrogen. So high analysis fertilisers are merely a substitute for plant diversity. So it's not really going to be that hard for us to wean off nitrogen once we start looking at plant diversity. I think I need to get a new mouse. We're having a mouse plague here in Australia at the moment, so maybe I can go and get one of those. The antibiodiversity experiment, I know I mention it every time. It's just because there is so much good research has been done there and so much great information. But when they looked at 1, 2, 4, 8 or 16 different plant species and 4 functional groups, the functional groups were grasses, legumes, tall herbs and short herbs, and the tall and short herbs were non-leguminous. And they looked at biomass production, beneficial insects, soil microbial activity, water balance, soil carbon, nitrogen. And this is just an overview of the site. But the one particular bit of this experiment that I want to talk about today is the nitrogen part of it. So with those different numbers of plant species, remember all 4 functional groups. So 8 plant species, for example, was 2 species from each of 4 functional groups. 16 plant species was 4 species from each of 4 functional groups, not just any 16 plants. And this is a multifactorial experiment where they've looked at 0, 100 or 200 pounds of nitrogen per acre per year. It was actually kilograms of nitrogen per hectare, but kilograms per hectare and pounds per acre are roughly equivalent. And it's multifactorial. So you might have just a monoculture with one species with no nitrogen, or 100 pounds per acre or 200 pounds per acre, right up to 16 plant species with no nitrogen, 100 or 200 pounds of nitrogen per acre. And what they found in this experiment was that if they had 8 or 16 plant species with no nitrogen, produced more biomass, like it produced a greater plant yield than 1 or 2 species with 200 pounds of nitrogen per acre per year. If you have a monoculture with 200 pounds of nitrogen per acre per year, it is not able to produce as much as a diverse polyculture with no nitrogen. And this result has been replicated around the world in many, many different experiments. There's research underway in Ireland at the moment, for example, looking at, mostly at pastures for sheep and for dairy and for beef cattle. And they're finding there that they can completely eliminate nitrogen through plant diversity. In fact, even something like 350 kilos of N per hectare, which is something like 760 kilograms of urea, per hectare. Like let's say nearly 800 pounds of urea per acre. Nearly 800 pounds of urea per acre cannot produce as much yield as having a plant community with 4 functional groups. I think this is really, I keep saying it and I'm going to say it again, the way of the future is going to be polycultures in every aspect of agricultural production. And I'll talk more about that next week when I'm talking about orchards and vineyards. So if levels of microbial diversity have been reduced in soil through, think of all the things that we do in agriculture, bare fallows, we don't have any photosynthesis, so we're not supporting any microbes. We use high rates of nitrogen fertiliser that we know throw the soil completely out of balance, inhibit root exudation, and if we've inhibited root exudation, then we're not supporting microbes. Fungicides, what are fungicides going to do to the fungal energy channel? Obliterate it. Pesticides are highly toxic. We really don't want to be using pesticides in agriculture anyway if we can avoid it. And inappropriate grazing management, which I'm not really going into in these webinars because we're talking about cropping situations. But if we are removing all the photosynthetic capacity of a pasture by overgrazing it, then there's not going to be enough carbon being channeled to the soil to support the soil microbiome. So within any of those situations, and those situations occur throughout the world in nearly all of our agricultural soil, biological nitrogen fixation is going to be inhibited. And that is why farmers have had to resort to using inorganic nitrogen fertiliser, because they have not supported the natural process in soil and probably haven't realised that even something like a bare fallow, for example, is going to have a hugely detrimental effect on the nitrogen dynamics in your soil. So how can we increase microbial diversity? In other words, how can we go the other way? Well, we just need to reverse all of those things. We need to make sure that we have year-long green, make sure that we never have bare ground. And we want that year-long green to be biodiverse. So we want a minimum of 4 plant families in our biodiverse year-long green ground cover. And we can also, particularly in the transitioning process, when we're weaning off nitrogen with amuse biostimulants, they're particularly effective on the seed because they're going to mimic the microbial signalling that will take place in a diverse sociobiome. So as I've explained in previous webinars, plants use chemical signals or biochemical signals to communicate with soil microbes. Microbes use biochemical signals to communicate with plants, and microbes use biochemical signals to communicate with each other. And those biochemical signals are going to be very rich in mediums like in the gut of an earthworm or in a fermented compost or something like that. We can just take a dilute extract of those kinds of materials and we will be taking out the chemical signalling molecules, or the auto-inducers, if you like, and applying those to seeds. We're not going to be applying microbes to seeds. We're just going to be applying the signalling molecules from microbes to seeds. And the seeds will interpret those as, they'll interpret that as they're in a microbially rich environment, and they'll produce lots of exudates to support those microbes and just kickstart the whole microbial diversity, just kickstart that whole process of plants supporting microbes and microbes supporting plants. If you have been using a lot of nitrogen fertiliser for quite a while, you're going to have very low levels of natural free-living nitrogen-fixing bacteria in your soil. They do take a while to replicate. With phosphorus, it's not an issue because the microbes that are involved in phosphorus acquisition can very rapidly build up in soil. It just takes the free-living nitrogen fixes a little while, something like about 3 years. So if you have been using a lot and you don't want your yields to decline, in the first year, it's best if you just reduce it by about 20%. But also, if you don't put it on the seed and don't put it anywhere near the seed. So you're going to reduce it, but you're also going to not put it in the soil. You'll use it as a foliar, or you will use an organic form of nitrogen like fish hydrolysate or something like that. In year 2, you can reduce it another 30%. In year 3, another 50%. So let's say you were using 100 pounds per acre. In the first year, you just go down to 80 pounds per acre. In the second year, you could drop it to 50. In the third year, down to 25 pounds per acre. And then indefinitely, if you feel that your plants do need a little bit of inorganic nitrogen, you can use 5 pounds per acre with no detrimental effects on the soil microbiome. So just to give you an example, 5 pounds of N per acre would be, say, 25 pounds per acre of sulphate of ammonia, because it's 20% nitrogen. So you need to look at the product you're using and what percentage of it is nitrogen. So when I say 5 pounds of N per acre, I mean of the N itself. The sulphate of ammonia is quite a useful inorganic nitrogen fertiliser to use because a lot of soils are slightly deficient in sulphur, especially if you're a long way from the sea. So it doesn't hurt. I'm not saying that all inorganic fertilisers are bad, and if they're used at very low rates, they're not bad. But what we are seeing in agricultural systems around the world is that in the early days, I don't know, maybe, the 1980s, 1970s, 1980s, people were using relatively small amounts of nitrogen fertiliser, and now they're using massive amounts. So over time, the amount that's being applied has been increased and that's because plants haven't been responding to it. So people have been put in a situation of putting more and more on, trying to actually get a response or even to maintain yield. So the idea is that we need to cut back, but you don't have to eliminate it completely. And if you can find amino forms of nitrogen, for example, fish hydrolysate, they're not going to inhibit the functioning of the soil sociobiome. But again, don't need to apply a whole heap. I think the application rate for fish hydrolysate will be something like 10 litres per hectare, which is probably about 10 pints per acre. We're not talking about putting gallons of this stuff on. And always use plant leaf tests to see whether your plants need nitrogen or not. And if they do, apply it as a foliar, only if they need it. And so over time, by cutting back, by introducing diversity, by making sure you never have bare soil, all of these things, it's like a jigsaw puzzle. You need to put all the pieces in place, and you need to monitor and see how you're going. And if you do leaf tests and your plants need nitrogen, then apply it, because we don't want you to be losing yield. But if you apply it as a foliar, it's not going to have an effect on the soil microbiome, and plants can take it up through their leaves. We just want to keep everything fully functional, and we just want to transition nice and smoothly into a situation where you don't need to use any at all, and you'll be building soil. That'll be one of the great things. You need to go out with a spade, dig holes, look to see whether your soil is aggregating, look for riser sheaths, all these positive things that over time will give you, as a farmer, incredibly positive feedback about how your soils are going and how everything is working together as it should in your soils. And you, as a person, will feel more connected to what it is that you're doing, rather than just going out, applying lots of fertiliser, then having to use fungicides, then having to use insecticides, then worrying about all the pests and diseases and the cost associated with producing a crop. And, you know, what if the price falls? What if it's cost me more to put this crop in than what I get back for it? It's a very stressful situation. And that situation can be just turned around to one that is a very, very pleasant experience, to actually see that you're building soil and that your plants don't need any inorganic fertilisers. So that's the end of my formal part of my presentation.